All right. Hopefully everyone can see the slides. Okay, let me go ahead and get started. This is joint work with Andrew Rhodes at Toulouse and Matthias Wildenbeest at Indiana University, who just presented. We're looking at the question of designing online retail platforms, particularly when sorry, I didn't do the full screen, particularly when algorithms are involved in the pricing process. Okay, so I think people understand that increasingly many products are sold through online marketplaces, often using something like the agency model, where it's the actual, call it manufacturers or sellers of the products that are setting the price through the platform. We also see an emergence of algorithms used to set prices. It's not the case that all sellers use algorithms, but it seems like a growing number do, and some of the largest ones do. There seems to be additionally a lot of evidence that this is probably growing. There are more and more firms, for example, that offer third-party algorithmic pricing software, often claiming that it uses, sophisticated AI and sometimes game theory, in fact. And there's a growing interest across the world, I think, in the role that algorithms are playing in a variety of situations, specifically in pricing, however. And indeed, there is some existing evidence. Klein and Calvano et al. Take some methods that are similar to what we use and show actually that algorithms can, in a sense, learn to collude on their own. There's also growing empirical evidence. Okay, so what are we going to do? We're going to look more at the platform side. Okay, and we see that platforms are basically firms that set rules governing how sellers interact on the marketplace, and these rules necessarily are going to have a big impact on the competitive outcomes on the online marketplace. Okay, so most simply, we can imagine platforms setting rules that influence which products that consumers consider, and perhaps nudging them towards some products or away from other products as consumers sort of search on the website. And we're also going to contribute, hopefully, to an ongoing policy debate, which is basically, what if any, responsibility do large platforms have in terms of designing their marketplace rules to be pro-competitive? Okay, so that's kind of where we're coming from. Specifically, what we're going to do is we're going to investigate how a platform can set rules regarding the interaction of sellers on its marketplace. We're going to consider actually some very simple design policies that involve demand steering. Okay, we're going to look at the theoretical effect. We're really interested in how the algorithms ultimately behave. Okay, so I am going to give some theoretical results, but we're ultimately really motivated by kind of seeing what the algorithms, in fact, will do. I want to emphasize that we're going to consider both competitive markets, okay, and also more cartelized or collusive markets. And we're going to see that our policies, their impact depends a little bit on what kind of market we're in. Our final takeaway, though, is that it does seem, based on our evidence, limited evidence, of course, that it is possible for firms to design policies, platform policies, steering policies that benefit both consumers and the platform, even if there's algorithmic collusion. Okay, as I said, I'm going to present some theoretical results. Ultimately, the interest is the algorithms. I'm going to do the theory a little quickly, I think, perhaps. Of course, especially given the time. I forgot to start my timer. Feel free to interrupt me at some point and tell me I should wrap up. There's two firms, okay, n greater than two firms. They are differentiated firms. It's important to keep that in mind. They sell on a monopoly retail platform. All the firms, all the sellers have some constant marginal cost that's inclusive of any platform fees, and they interact repeatedly over an infinite horizon. Okay, in each period, what happens is firms observe all the past prices, firms set their prices. Okay, there's a common discount factor delta regarding kind of how valuable the future is. On the demand side, in each period, a new cohort of consumers arrives. They want to buy at most one of these differentiated products. They've got some utility system that I'm not going to give you the details of, but it generates a very standard logit discrete choice system with what I'll just call a differentiation parameter mu greater than 0. And then the platform basically commits to a rule regarding how it's going to display products based upon the set prices. And then consumers either buy a product or they walk away. All right, so that's the basis of the theoretical model. We're going to specifically look at two design rules, two steering rules that the platform can use. The first is called price-directed prominence. And the idea behind PDP is very simple. In every period, the platform just looks at the prices that are set by the firms and chooses K of the firms that have the lowest prices with some random tie-breaking rule, where K is less than N, right? So there's a total of N firms, so K is some fixed integer less than N, and basically in every period, again, the platform just looks at the prices and shows the firms with the K lowest prices to the consumers, okay? What happens with this policy? It's a pretty simple policy, right? It says we're only going to show low price firms. Well, let me first of all say that if we don't have this policy, so if we just let the firms set prices however they want, and if we also assume that the firms are not cartelized, so they're just kind of, setting prices in each period to maximize within period products, then we have a simple result, which is because there is product differentiation, firms set a price greater than marginal cost. Okay. However, once PDP is implemented, okay, basically prices are driven down to marginal cost. And there actually is a bit to the proof, but I think the intuition is pretty clear. If you're one of the higher priced firms, you're just not shown to consumers, right? So now you have an incentive to lower your price to try to be amongst the K lowest priced firms, and that builds up and leads to marginal cost pricing. Now, that's not necessarily good for consumers because remember products are differentiated. So there's a trade-off between lower prices following the implementation of PDP and lower variety. But what we can show is that, as long as you show enough of the firms, but not all of them, as long as you show enough of the firms, then basically consumer surplus increases in this environment. Okay, so that seems to be good. Of course, we are assuming that the market is competitive so far. And if we assume the opposite, disappointingly, we get a very different result. Okay, we actually, if we sort of redo the analysis, but now we suppose that all the firms, the sellers are colluding, and that the discount factor is high enough that they can, collude successfully. Then actually, what we show is that when you commit to this policy of price-directed prominence, the prices don't fall enough to overcome the loss of variety. So basically the cartel is strong enough that it does lower prices, but not enough. And so actually we find that this policy harms consumers when the market is cartelized. So we immediately see that from a theoretical standpoint, it's not even clear what the effect of this seemingly simple policy should be. We have one more policy I'm going to talk about, and then again, I'll get to the experimental results. So the second policy is basically motivated by the fact that it seems that the simple policy doesn't break collusion. So we say, well, what if we make a policy that's a little more complicated? And I'm not going to step through all the details of the second policy. I have them listed right there. You can read them if you're interested in all of the details. I'm just going to explain the intuition behind this second policy. The idea behind this second policy is to reward firms that cut prices, okay, not just in the period in which they cut prices, but also in future periods, okay? So in particular, what we do in a way that's spelled out precisely on the slide, if you read the details, what we do is we basically give what we call a pricing advantage to a firm that charges a very low price today, and that pricing advantage makes it harder to steal demand away from that firm in the future. Okay, basically we give that firm some special advantage. And the main result that I want to emphasize is that it turns out that even as delta becomes very, very high, so even as firms become infinitely patient, okay, if you implement this policy, okay, correctly designed so that this value, this fixed value ADV is large enough, then actually occlusion becomes impossible. So that in any pure strategy, subgame perfect Nash equilibrium, the transaction price is marginal cost in each period. And again, the intuition is the main thing I want to emphasize here. Dynamic PDP, which is what we call this policy, it makes collusion harder because it makes it harder for the cartel to punish firms that cut prices. So basically, the way the policy works is if you deviate from the cartel pricing today and lower your price enough, then we, the platform, are going to give you a pricing advantage that makes it harder for the cartel to punish you in future periods. Okay, and so this can benefit consumers under a large variety of parameters. Okay, so that's the theory. Again, what we have so far is two different policies: price-directed prominence, and then a more sophisticated one called dynamic price-directed prominence. And we see that there are potentially some good theoretical properties, but it depends a little bit on whether the market is cartelized or not. So what are we going to do now? We want to look at the AI pricing experiments that we run. I imagine that some people are familiar with reinforcement learning. Due to the time of the talk, I can't give all the details about it. I just want to emphasize that we're using an approach called Q-learning, similar to what Emilio and his co-authors and Timo Klein have used. And Q-learning is a popular approach to reinforcement learning or artificial intelligence from the computer science literature. It's perhaps most famously used by DeepMind, I guess. Alpha's DeepMind, or AlphaGo is what I should have said. Google's AlphaGo project to be, some of the best Go players in the world. Okay, so it's a very sophisticated technique. We're using a very much simpler version compared to, of course, what Google used. But it is a common technique, and the thing to emphasize is that Q-learning, this approach to reinforcement learning, doesn't really impose any structure on the problem for the algorithms. That basically the algorithms, they go and they experiment and they quote unquote learn over time and converge to some equilibrium. Okay, so that's what we're gonna look at. Just to give you a few more details, I'm not going to give you all of the details, again, due to time constraints. We have this parameter gamma that's really important. Okay, gamma is the percentage of consumers that are subjected to the platform's policies. So basically, if gamma is equal to 1 and we're implementing PDP, that means 100% of consumers are only shown one of the K lowest price firms. Whereas if gamma is equal to 0, the policy binds on no consumers and every consumer sees all end products. So basically, as gamma gets higher, we're implementing these policies on a larger subset of consumers. Okay, and that's what we're going to look at, basically how gamma changes and how that influences outcomes for two different levels of price, of product differentiation. Mu equals 1/20 and mu equals 1/4. All right, let's just jump right in. What happens? The parameterization's at the top. This is two firms, large discount factor, mu equals 1/4. On the left-hand panel, we see that as we increase gamma, so as we go along the x-axis here, we're implementing the policy on more and more consumers. The price goes down eventually, which seems good. Unfortunately, if we look in the right panel, we actually see that ultimately consumer surplus is lower than where it started at. And what that means is this policy, although it's lowering prices, it's reducing variety enough that consumers are actually worse off. Okay, so even though prices go down, it's not helping consumers. This is consistent with the theory I gave you a few minutes ago about how PDP should work in cartelized markets. Okay, it sounds like maybe the policy should work, but when markets are cartelized, actually it seems that maybe it's not so simple. And I have a similar graph, well, different actually, in an important way. This is now when mu is equal to 1/20. Okay, so the products are much less differentiated. Here we see with prices a similar pattern. Prices go down. Okay, they go up a little bit at first, but then they go down. However, a consumer surplus also goes up quite a bit. If you look at the right-hand panel, you see actually this implementing this policy has a very positive effect on consumer surplus. Okay, so this is now different from what theory suggests. This seems to be more in line with what we would expect when the market is competitive, which is this technique seems to be working well, raising consumer surplus by quite a bit. Again, because of time, I'm going to focus for the rest of the talk on the case of high differentiation. Remember, with high differentiation, mu equals 1/4, it seems that the regular policy of PDP actually harms consumers, at least when the discount factor is high. what I want to do is look at the outcomes when the discount factor is varying. And I'm going to actually direct your attention to the right-hand picture here. And on the y-axis, we have the discount factors. And the way I'd like you to read this graph is to choose your favorite discount factor, maybe it's 0.5, and then look at what color that is. It's always green, okay, the way we made the graph, it's always green to start with. And then just read to the right, and if the colors get more red, then consumers are better off, okay? And you can see by how much in the legend over here. And the takeaway here is actually that except when delta is very, very high, like way up here, only when delta is really, really high does this simple policy harm consumers. Otherwise, consumers are always gaining, at least if you raise gamma to a high enough level, okay? And sometimes these gains are really quite enormous, okay? So we think this is encouraging, that this policy, this simple policy may work pretty well, okay, depending on how the algorithms are exactly programmed and how they discount the future, okay? But of course, perhaps collusion is a significant concern, okay? Emilio and others have shown that could certainly be. So now we're gonna look at our second policy, dynamic PDP. Remember, this is the one that's specifically built to try to give an extra advantage to firms that cut their prices. It's specifically built theoretically to fight collusion. And here we can see what happens in the left-hand panel. We see what happens. The red line is prices under this dynamic PDP policy, and you can see that prices go down a lot. And this is all compared to the simpler policy, which is in blue, okay? So we see that this new dynamic policy has a huge effect on prices. There's a little quirk at the end. And in terms of consumer surplus, it has an enormous effect on that, positive effect on that as well. So remember, this is with mu equals a quarter. The standard policy of PDP, which is in blue, remember, it is actually bad for consumers, whereas this dynamic policy is very, very good for consumers. And so what this means, what this suggests is that on the one hand, algorithms are really good at colluding, but you can design policies that seem to make it pretty hard for them to do it, but these policies need to be a little more subtle than just showing the lowest priced firms. I'm not going to talk about this learning challenge just because of time. Not quite sure how much time I've even used. So again, just tell me. Actually, I think that was our last slide. Okay, so I'll slow down and give you just 1 or 2 more minutes if that's okay. I think I did okay here. Just talk a little bit about this learning challenge. I think it's interesting because if we were to be serious about trying to design a platform to counter algorithmic collusion, we have to understand that sometimes algorithms behave a little differently than we might expect. You might have thought that when you make gamma equal to 1 so that all consumers are subject to this policy, that prices would keep going down, consumer surplus would keep going up, but it actually seems that the algorithms get confused. We have some speculation about that. Very briefly, we think that it has something to do with what we call sort of local learning of the algorithms that we think is essentially shut down here. Probably wasn't clear. It's in the paper, okay? Just to kind of talk briefly about some extensions and then wrap up. The main thing I want to talk about is the platform profitability down here at the bottom. We look at how platforms may benefit or not benefit, and actually what we show is that depending on the platform fees, whether they're kind of per unit fees or revenue sharing fees, that actually the platform can benefit as well, so that some of these policies can benefit consumers and the platform itself, which we think is encouraging. At least to us, that seems like a positive development. This is especially true when revenue sharing is used, or sorry, actually I think it's when per unit fees are used. We would point out that a lot of marketplaces these days, online marketplaces, have fulfillment services that are based on per unit charges. So we actually think that per unit case is pretty important. Just to conclude, should large platforms have a duty to design pro-competitive rules? We don't answer that question, but we think it's an important one. We looked at design rules that steer demand to certain firms based upon those firms' prices. These policies limit choice. But in some cases, they nonetheless benefit consumers because of the additional price competition that's fostered. However, when the markets are cartelized, okay, so when the algorithms behave very collusively, you need somewhat more subtle policies such as dynamic price-directed prominence. The bottom line is it seems that it's feasible, perhaps, for a platform to design rules that bolster competition, benefit consumers, and even raise platform profits, and even if pretty sophisticated pricing algorithms are used. Thank you.